SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. So, last time what we did was that we discussed about the complete droplet evaporation model, and we looked at that the flow field within the droplet resembled like the Hill spherical vortex, and then we solved the entire transient energy equation, okay, including the convective terms, and we showed that how this is to be solved numerically essentially, and we will discuss some of the results here. Now, there is one more alternative approach, sorry. So, there is one more alternative approach, and this approach is basically called the effective conductivity model. Effective conductivity model. Now, what does it do essentially? Okay. So, what it does is that instead of using the actual conductivity, the thermal conductivity, it uses an effective value of the thermal conductivity. So, your K effective will actually be some factor x or chi terms the liquid conductivity. This factor is usually much greater than 1, or not much greater, it is actually greater than equal to 1, so to say, it is like greater than equal to 1. Okay. So, what the approach essentially entails is that what does convection essentially mean? Convection means that it enhances, right, the energy transport within the droplet. Okay. Now, in this particular case, the energy transport within the droplet is, because it is enhanced by convection, as we saw the Peckley number is high and things like that, but the essential spirit of the whole thing is that if we can somehow designate that convection effect by enhanced thermal conductivity, then perhaps we can get around solving this complicated transient equation that we did in the last lecture, okay, which involves the Peckley number and the convection terms, right. Can something like that be done in this particular context? So, that was what the main spirit of this thing was. So, what Kronig and Brink did was the following. They found that at high Peckley number, okay, and at tau approaching infinity, that means at long time scales, okay, the overall heat and mass transfer, and this is an important statement, the overall heat and mass transfer rate, okay, between the droplet and the surface, between the droplet core and the surface, okay, is about 2.72 times higher than an equivalent solid sphere. Understood? So, that means it basically implies that this factor chi that we talked about is about 2.72, right. So, what did they find? They found that at high Peckley number and high time scales, the heat and mass transfer rate is basically 2.72 times higher than an equivalent solid sphere. Okay. So, this triggered the thought process that if we could use thermal conductivity, right, which is about 2.72 times, then we are kind of okay, right. So, ideally this 2.72 is like a misnomer, it actually should be a function of the liquid phase Peckley number, right. So, if the Peckley number is high, that means you will have more thermal conductivity, you have to use a value of the thermal conductivity. So, the overall formulation that they gave, it was about 1.86 plus 0.86, this is once again nothing but a sophisticated curve fit, 2.245 log base 10 Peckley number divided by 30. So, this comes basically from curve fit. So, that you should not be under any misconception. Okay. So, if you evaluate this factor depending on the liquid phase Peckley number and you use that factor to enhance the thermal conductivity, the effective thermal conductivity, then you can get away just by solving the spherically symmetric heat conduction equation, right, that you do for a normal solid sphere. For a solid sphere there is no convection. So, inside the solid sphere you can just use the spherically symmetric heat conduction equation. Here also you can do the same, okay, but using an effectively higher value of the thermal conductivity, okay. But this is a function of the Peckley number, okay. And if you look at now a small plot for the same, if I try to draw this is say the two axes, let us put 2 marks over here, this is 10, this is 100, this is a log scale, this is 1000, this is 1 and this is 3. Okay. So, it shows something like this. This mark is about 2.72, got it. Okay. So, you can see initially for low enough Peckley number this is almost there, right. For high enough Peckley number it lies somewhere in that intermediate region, and for very high Peckley number limit it actually goes somewhere to around 3, okay, close to 3, that is 2.72. That is how this particular thing actually works, got it. So, the effective thermal conductivity model, and we will see some examples, this usually is formulated to avoid any computational overhead and things like that. So, that we can get around the problem, right, pretty simply, okay, and that is the whole criteria for doing this kind of an analysis. Okay. So, the effective thermal conductivity model saves on computational time essentially, computational time. It can also help you to do quick back of the envelope calculations. Envelope calculations. Okay. So, those things becomes vitally important. Okay. Now, let us look at the presentation now, because we are supposed to discuss some of the results. Okay. All these results are from Abramson and Scirinniano, and in fact, the presentation that the material that we covered is mostly from Bill Scirinniano's book and Abramson and Scirinniano's model. This is a very famous model and it is widely used, okay, in the literature. Okay, people to this day actually use this model with slight variations here and there, but mostly the basic framework is still the same. They still use the Hill spherical vortex, they still solve for the external flow field, okay. And we will see that this is actually a very effective thing. It matches with experimental data, though it is an approximate model because the liquid flow field is actually not solved, okay, completely inside, but still it gives you a very good idea. And as you know that the liquid flow field has been evolved through the calculations, right, involving the Faulkner scan type of solutions. Okay. Now, let us look at some of the results which will try to give you an idea that what is exactly happening. So, this comes generally, we said that the model can be solved numerically. This is basically the numerical solutions that you see over here. Okay. So, this should be interesting. So, here some of the basic parameters are T naught, the initial temperature is 300 Kelvin. This can be anything, you can actually do your own model, okay, but this is just to give you an idea. The external temperature is about 1500 Kelvin. So, that is more like a flame and things like that. The external pressure is about 10 atmosphere. So, it is a high pressure chamber. The initial droplet radius is about 50 micrometer. 50 micrometer is roughly half of a human hair, size of a human hair, and the initial velocity of the gas phase flow field is about 15 meter per second. Okay. So, these are the conditions that are actually given to you. Okay. Now, let us look at each of the figures very carefully and try to see that what the things are. And if you watch it now, there will be now, if you will see here there are curves like 1, 2, 3, 4, right. So, 1 is basically the current model that we are talking about, right. This is this model, that is the Sheriniano's and Abramson's model. Okay. Infinite conductivity model, we already told you that that is 2. 2 is basically infinite conductivity model, which we already said KL approaches infinity, right. So, that is the infinite conductivity model. Okay. And effective conductivity model is 4, which we just now said that K is now equal to chi into KL, right. So, that is the effective conductivity model that we just now said. Okay. The extended model, infinite conductivity, and then the third is basically number 3 is basically the conduction limited model. Okay. The conduction limited model. We already covered this, that what is a conduction limited model, right. Got it. Okay. And what it says is that it shows the non-dimensional radius versus time, right. This time is the raw time, okay, for that 50 micron droplet that was injected. Non-dimensional radius is basically r by r naught, that is why it starts from 1 and goes all the way up to 0.2 and things like that. Okay. So, if you see now, okay, 1 and 4 comes very close to each other. Okay. 1 is basically the current model, is the vortex model basically, right. Okay. And 4 is the infinite conductivity model. So, they pretty much predict the same thing, right. While on the other hand 3, which is a conduction limited model, okay, slightly underestimates the decrease in the droplet diameter. Underestimates means it takes a little bit of longer time, right. That is 3, conduction limited model, and 2 is basically where it is the other side of the spectrum, that means it is a very high level of thermal conductivity, right. So, it is natural that our results will fall somewhere in between these two limits. Why this number 3 will be slow? That is because it is conduction limited, right. So, the only way that heat is being transferred within the liquid phase is through conduction, right. Through conduction it is happening through the liquid phase, right. So, this is basically only conduction. So, K is basically equal to KL, and here you have KL is approaching infinity, right. So, our convection or the infinite conductivity model has to fall somewhere in between these two limits, right. So, that makes physical sense, right. It cannot be anything else, it has to fall within the two limits, because one is predicting very high thermal conductivity, that means whatever is the temperature on the surface of the droplet, that is the same temperature inside the droplet, that is your effective thermal conductivity model, right. Because this should imply that T, okay, is not a function of space anymore, it is not a function of r, right, it is not a function of the droplet, okay, it is only a function of time, right. So, this would naturally imply that you are assuming a very high level of heat transfer that is happening within the droplet, because the entire droplet is getting to the same temperature, right. Whereas, in the conduction limited model it completely ignores the convection effect, right. So, here you will have a temperature which is higher at the surface and lower at the center. So, it will be more like this, right, higher at the surface, more at the center, right. So, that is this model, right. So, you have a temperature gradient inbuilt, right. In this case the temperature is the same everywhere, right, same everywhere, correct. Okay. And these two model, convection and the effective conductivity, because they are pitched against each other, they pretty much do the same thing, right. They try to bring in the actual effect into the picture. Okay. So, they should lie in between these two extreme limits. I think that part is clear now, correct. Okay. So, let us look at the surface temperature on the other hand, based on the different types of models that we have over here. Okay. Now, if you look at the surface temperature, once again 1 and 4 you should recall 1 and 4, 1 is the vortex or the extended model, okay. 4 is the effective conductivity model, effective K model. So, once again you see 1 and 4, okay, they are very close to each other, you see that they are very close to each other, 1 and 4, right. 2 shows that kind of a profile, 3 shows that kind of a profile, okay. Now, once again here what you see, if you go back and just see what is 3, 3 was the conduction limited model, right. So, 3 is conduction limited, okay. and 2 obviously is the infinite conductivity. This is the infinite conductivity. Got it? Now, the question is that when there is an infinite conductivity, you can see that this rise of the droplet surface temperature is rather slow, right, and it is going up to a value, okay, at a much later time. If you plot it by the time axis, it goes at a much later time, right. Got it? Okay. Whereas on the other hand 3, which is the conduction limited model, goes to that surface temperature at a much smaller time. This is also obvious, think about it, because the entire droplet is now at the same temperature, right, but the heat that you are supplying is still the same, is not that so? It is still Ts minus T infinity, whatever is coming, right, Ts minus T infinity from the gas phase, right, whatever is conducted into the liquid, right. So, Ts minus T infinity that, so if your surface temperature and your liquid temperature inside core temperature are the same, naturally it will take more time for this entire thing to pick up, right, okay, because you are heating the whole droplet. In this case you are heating basically the surface and some heat of it is basically getting conducted inside. Okay. So, that is the reason why you have this slight disparity, okay. But all of them, as you can see, more or less shows a flattening of temperatures, say around 520 to 500. Okay. So, that is called basically the wet bulb limit, as you already know by now, that is what we have explained earlier. But 1 and 4 there is nothing much to choose between the two. That also shows that these two models are very effective to each other. Okay. Let us look at the transfer numbers now. Okay. So, what are the two transfer numbers we have? We have Bt and we have Bm, right, these two transfer numbers, that is the Spalding heat transfer number and Spalding mass transfer number. Okay. Now, we said that they have to be less than 20, right, for this model basically to work, right. So, you can see that both of them actually goes up, okay, and they actually flatten out towards the end of the cycle. So, Bm actually flattens somewhere around 8, Bt flattens somewhere around say 15. Okay. So, the heat and mass transfer numbers actually, okay, go up, okay, with the flow, with time. Okay. Now, this is the interesting part where we look at the Reynolds number, right. Previously we said what, if you recall, that this Reynolds number is greater than equal to the Reynolds number of the gas phase. Recall, that is what we said, right. The gas phase Reynolds number uniformly comes down, it has to, that is because this Reynolds number is dependent on u infinity minus u, right, and this is the relative velocity between the gas and the droplet. So, naturally this should come down with time, right, because the gas and the droplet, okay, so they will, so it is like if you inject a droplet in a stream, right, what happens to the droplet? The droplet is accelerated and ultimately approaches the velocity of the gas phase, right. So, their relative velocity kind of comes down. So, as their relative velocity comes down, what will happen is that this Reynolds number of the gas phase should also come down, right. So, this Reynolds number of the gas phase therefore comes down with time. So, it starts with a value of around 100, it comes to very close to 10, 5 etc. with time, right. The liquid phase Reynolds number, however, shows different characteristics, okay, slightly different characteristics. So, it initially goes up and then it kind of comes down. Can you imagine why? Because the liquid phase Reynolds number will go up, that is because when the droplet is actually accelerated, right, because liquid phase, this is a function of us, right, the surface velocity, right, and if you recall, the surface velocity was a function of Cf, it was a function of the Reynolds number and all those things, right, it was a function of the delta u, right, if you recall. So, this us therefore, okay, initially when the droplet is accelerated, this goes up, and then as the relative velocity comes down, this slowly comes down in a profile like that. Got it? Okay. So, that is the nature. As you can see, this Reynolds number is at least 5 times higher than the gas phase Reynolds number, mainly because your rho L is 1000 times your rho V essentially, or rho gas, okay, whatever you call it. Clear on this particular part? Okay. Now, the other important part is the Peckley number, right. See, we used the vortex model mainly because of our Peckley number issue, right. So, the Peckley number, we said that because Peckley number is of the order of 100 and sometimes even more, sometimes of the order of 1000, okay, we have to use the convection, right. That was the whole logic, right. And we also said that the Peckley number is the one that actually determines what kind of a mode of heat transfer one would have, right. Is it convection dominated or is it conduction dominated, right. So, if you look at the profile of this Peckley number, this is very interesting to say the least, right. Peckley number, as you know, is a function of Reynolds number and Prandtl number, right. So, liquid phase Prandtl number is of the order 10. So, naturally whatever is the value of the liquid phase Reynolds number, it is multiplied by 10, right. So, if the liquid phase Reynolds number is 300, this will be like 3000 of that order, right. So, here if you look at it as the Reynolds, it mimics the similar profile as Reynolds number. If you look at it, it is similar to this Reynolds number kind of a profile, right, because Prandtl number is kind of uniform, so to say, right, unless you take into account the property variations, it is more or less uniform. So, it should mimic a very similar kind of a profile. Now, here you can see there are several distinct stages that we can identify, right, if you look at this particular figure very carefully. Here you will find that initially at the very initial part of the time, that is very small time instance, right, and we will see what happens. Your Peckley number is actually low, very initially when it is just picking up, right, in that few less than a millisecond, okay, it is actually going up, right. So, it is going up from some value, right. So, it is a very sharp rise. So, here Peckley number is low. If Peckley number is low, here we can expect that the heat transfer will basically be conduction dominated, right. Okay. In this region, that is from this point all the way up to say about 100 up to about this point, in this large region, okay, the Peckley number varies between say something like 1000 of the order 1000 to the order 100, right, 110, things like that, right. In this part it will be a convection, we can expect that it will be convection dominated, right. So, that means the isotherms that you are going to get will mimic the streamlines, right. Here in conduction dominated, the streamlines and the isotherms will be different to each other, right. But here of course, because it is convection dominated, okay, the streamlines should now be the similar to the isotherms, okay. But towards the end, towards this last stage, this tail of the distribution, the Peckley number once again becomes low, right. So, here you can think about that there is a re-emergence of conduction, there should be a re-emergence of conduction, right. So, how can we validate this? Just by looking at the temperature profiles inside, right. If you look at the temperature profiles, then you know what is going on, right. So, let us look at the temperature profiles like this, okay. So, this is half the droplet, this other half is symmetrical, so it is not drawn, right. So, what is happening here is the first 0.025 milliseconds, the very first few instants, you can look at it here, it will be somewhere there, right, very first few milliseconds, not even milliseconds, it is like sub milliseconds, right. So, this is more like 250 microseconds or 25 microseconds, and think about it as microseconds, right. So, what is happening over here if you look at it, okay, the liquid isotherms in this very short time, the heat is basically transferred by thermal conduction, right. This is basically heat is supplied by thermal conduction, mainly by thermal conduction, right. So, you can see that the isotherms, okay, these are the constant temperature contours, they do not mimic the flow, because the flow is like a Hill spherical vortex, right, it is like that, correct, it does not show that, it is just this kind of a typical diffusion dominated problem, right. Okay. Now, when we go to say beyond 0.05 milliseconds, so when the time is now greater than 0.05 milliseconds, actually we are showing an instant of 0.1 second over here. Okay. You can see that the temperature profiles now start to mimic, you see these temperature profiles, they start to mimic the streamlines. Do you see that? These are the isotherms, they are mimicking basically the streamlines, right. So, they are mimicking the there is a distortion of the spherical symmetry of the temperature field. Okay. It starts to mimic basically the isotherm the streamlines. So, the temperature profiles start to mimic the isotherms, right. So, they start to mimic the isotherms, you can see it very clearly, the isotherms are being mimicked in this particular way, right. They are starting to mimic the isotherm, right. Okay. So, from here and here, these are the two instances where this has started, this has just started, here it is completely so these isotherms now extend all the way to that direction, right, and curve up. That is what you see, right, when you go from here to here. This is at a later time instance like 0.1 seconds, is not that so, right. So, that is obvious, because in these cases the Peckley number now is of the order of 1000, okay, and that you can see from the previous plot itself, right. Peckley number here is of that order, it has sharp rise in Peckley number, right. Now, say up to at 3 milliseconds you basically see the same thing, the liquid isotherms are like that, right. So, they start to mimic the flow field. Okay. After about 5 milliseconds, that means this is 3 milliseconds, after about 5 milliseconds, which is this 6 millisecond is a good enough example. Okay. You can see this at this particular point your Peckley number falls below 100, right, that you can see over here also. So, this is 5 millisecond, right, that is the point, right. So, after 5 millisecond what happens, your Peckley number has already fallen short, right, it has already fallen short of that 100 mark, right. So, as it starts to fall, do you see that these streamlines have now started to show the reverse transition, right. So, they have started mimicking the conduction from convection to conduction. So, they have started to show the, because you see once again the streamlines are curving down like this, right, is not that so, it has started to, it is no longer like that extending all the way, right. So, it is basically a reverse transition, that is because the Peckley number here has fallen below 100. So, naturally the conduction and convection, okay, convection to conduction transition has started to happen, and the streamlines or the isotherms have clearly showing deviations from the streamline pattern, right. So, this is showing deviations from streamline patterns, right, started to show those deviations, right. Here of course, it mimics the streamlines, right, got it. This part should be very clear to everyone. Okay. So, now in the next lecture we will see what it does to the mass vaporization rate, and before we move on to the other topics, but this actually should be clear that there is first there is the conduction, okay, then this shows the transition from conduction to convection. This is full convection, and then it starts to show the reverse transition from convection to conduction. So, this profile and this profile in a time limited sense they are kind of similar looking, you can see that, right. These streamlines are curving like this, but it is basically like a hysteresis, that is the that is conduction to convection, this is convection to conduction migration, right. That is what is happening in these two cases. Okay. So, in the next lecture we will going to cover the rest of the topics. Okay. Okay.